Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. My science fair project is about electric motors, electricity, and magnetism. I chose this project because I wanted to know how electric motors worked. This is important because a lot of companies have started to make electric cars, and if we can make more efficient and powerful motors, there will be no need to make heavily polluting gas cars. First, I did some research on how direct current motors worked. I found they use an electric current passing through a coil of wire to create an electromagnet, which is attracted and repelled by a permanent magnet. The electromagnets are turned on and off continuously to maintain the rotation as shown on the animation on the right. If we can make the electromagnets very strong, this will increase the repulsive and attractive forces between the magnets, making a more powerful and faster motor. Based on my research, I found that the strength of the magnetic field B in the coil is dependent on the current I, the number of loops N, and the radius of the coil R, according to the formula shown in figure 1. Therefore, we can increase the strength of the magnetic field by increasing the number of loops in the coil. Because of this, I predict that the coil with more loops will spin faster than the coil with less loops. The materials needed to create my experimental setup are listed here. You can pause the presentation if you would like to review them in detail. First, cut 2 pieces of the 14-gauge copper wire about 28 centimeters long. Use pliers to bend the copper wire as shown in the image at the top left. Next, attach your 2 copper wires to the D battery using some zip ties. Then, connect some alligator clips to the wire and connect it up to a multimeter. Then, use your enamel wire and wrap it around a D battery. Count the number of loops, and when you're finished, you should have a coil that looks like this. Next, sand one end of the enamel wire until you can see the bare wire. This is because when the bare wire touches the 2 copper wires, it will conduct electricity through the coil, which will generate an electric field. When the coil turns, then the enamel coating on the wire will act as an insulator and the electric field will disappear. As the coil spins, the magnetic field turns on and off. When the magnetic field is on, it is repelled by the permanent magnet, causing it to spin. Measure the distance between the coil and the magnet. Keep it the same for all your tests. Then put some reflective tape on it so that you can record it in slow motion. You will also need to record a stopwatch in slow motion. This way you will know how much recording time 10 seconds is in real time. This will allow you to calculate the revolutions per minute. I created many loops with different diameters and different number of loops. Since cell phones have a compass, I figured they would have a way of measuring the magnetic field to find north. I searched for an app that could use the sensors on the phone to measure the magnetic field strength. During the experiment, I observed many interesting things. I noticed that the voltage dropped every time the motor turned. With a higher number of loops, I could feel a stronger magnetic field when I held the permanent magnet next to it. This table shows the data I collected during the different trials. I repeated each test a couple of times and took the average results. At very high revolutions, it became very difficult to count the number of loops, even in slow motion. So I used another camera to record the slow motion video, slowing it down even further, and counted the revolutions over 10 seconds. I always counted the revolutions from the last 10 seconds of the video. This way, I was always collecting the measurements when the motor was at full speed. I plotted a graph of the RPM and the magnetic field strength against the number of coils. The graph is shown on the right. The results showed that as the number of coils increased, the magnetic field strength also increased. However, the RPM decreased. This was a very puzzling result, contrary to my hypothesis. Next, I plotted a few graphs to analyze the effect of coil diameter on the RPM and the magnetic field strength. I noticed that with smaller diameters and the same number of loops, the motor spun faster and the magnetic field strength also increased. I believe this is due to the lighter weight of the smaller diameter coils and the stronger magnetic field strengths with the smaller diameters. Based on the results, my hypothesis was proven incorrect. The motor with less coils spun faster than the motor with more coils. However, the magnetic field strength was stronger for the coils with more loops. I believe the motor spun slower because the weight increase of adding more coils was greater than the force created of the magnetic field strength, as shown with the smaller diameters. Based on this information, I would need to use a very thin wire with many loops. This way, the increase of the magnetic field strength created by adding one loop would be stronger than the weight increase by adding a loop. Through the project, I also tried a few other things, like creating a commutator and using AC current to alternate the magnetic field of the coils, the details of which are shown in this slide. Jazakallah, and thank you for listening to my presentation.